Okay, let's get started with an example. Just make sure we can handle hypothesis testing for means. Okay, so let's do. Let's say you obtain a random sample random sample of 25. What are we measuring here? We'll look at butterflies. Because who doesn't love butterflies? Okay. 25 butterflies of a particular species, sure. I don't know. Whatever species, Lepidoptera, something. Okay. And then, and we measure, let's say, the wingspan of these butterflies. Okay. The mean length, mean wingspan is making stuff up. Let's see, 4.68 centimeters with a standard deviation of 0.82 centimeters. Okay, and then we ask, do we have evidence that the mean wingspan I guess these are tiny butterflies. Of all butterflies of this species, is over, we'll say, 4.5 centimeters. Okay, so we'll say calculate the p-value. I have to do my calculations myself here. Let's see. Okay. All right, and we'll say, okay, your answer choices are p-value is less than 0.001. B is that the p-value is greater than 0.001, but I think the, let me just double check where my, you'll need your t-table. Oops. .005, .010. Okay, I hope the correct answer choice is available. Oops, I might have made a mistake. Oh shoot, I probably, hang on. gotta revise this. I don't have the number's not big enough. Okay, hang on. Edit, undo. So I got, I apologize. All right, we'll just we'll bracket it off like this. Let's start a session. Okay, I'll leave the thing open, all right? You can change your answer as I give you the answer. Okay. Okay, so what we're going to do is we're going to calculate the p-value. It was kind of funny when I said, can we do this? And you guys all said, no. All right, so our first thing we're going to do, we got to figure out our standard error, okay? Well, I guess first we should set up our hypotheses. So how would we set up our hypotheses? We would say mu is equal to, we're going to say mu is equal to 4.68 or 4.5. Okay, so the question is, do we have evidence that the mean wingspan of all butterflies is over 4.5? So this is kind of the claim that we are testing. So we're going to say mu is equal to 4.5. And our alternative, because it says over, is going to be mu is greater than 4.5. Is that okay with everybody? Okay. Step 2, we're supposed to check conditions, and we'll just say conditions are met. Okay, large sample, we've got 25 or more, so that's great. And then everything else, we got a random sample. There are obviously more than 250 butterflies in the world, so we're okay. Well, I don't know. Maybe this is a particularly endangered species and there's less than 250 specimens. Then we'd be in trouble. But, okay, standard error. We're going to do S divided by the square root of n. So I have 0.82 divided by the square root of 25. And my standard deviation, 0.82 divided by, I have 0.164. This is my standard error. So far, so good? Okay. I got to get my test statistic. In this case, it's going to be t. T is x bar minus the value in my null hypothesis divided by the standard error. So my x bar, the value that I found, my sample mean, is 4.68. We're going to subtract off my mu 0. What's my mu 0? It's the number in my null hypothesis, 4.5. And we're going to divide that difference by our standard error. Okay? Effectively, we're asking, if this null hypothesis were true, I would expect my sample averages to be around 4.5. I observed 4.68. Is that a big difference or not? Okay? So we're comparing 4.68 versus 4.5, and we say, okay, well, that difference is 0.18. Is that big? Big depends on our standard error. Our standard error is 0.164, so 0.18 divided by 0.164, our difference is 1.0976. All right, this is our test statistic. Okay, we're about one standard deviation, a little bit more than one standard error away from what we expect. Okay, so we would look this up in the t-table with 24 degrees of freedom. So when we go to the t-table, 24 degrees of freedom the very first number I see is 1.318. Okay? So I have degrees of freedom equal to 24. We go to the t-table. So at 24 degrees of freedom, the very first number is I already forgot what I said, 318. Okay? 1.318 corresponds to a tail area of 10% if we go to that column. Okay? And what we see is that 1.0976, this fits right here, this is smaller than 1.318. Therefore, my tail area is going to be what? Greater than 0.10. Okay, so at this point I have my tail area is greater than 0.100. So far so good? Is that okay with everybody? All right, and so the question is, how does my p-value relate to my tail area? Okay, well, we look at the alternative hypothesis, and actually this is my right tail area, so then my p-value is equal to my right tail area. Therefore, my p-value is greater than 0.10. And there you go, there's our answer. Okay, so you can update your remote clicks to reflect that. Before I go on, I want to make sure, are there any questions as to any of these steps? Yes, question.
If this was like a two-sided hypothesis, just double.
Yeah, if it were two-sided. So if the question says, do we have evidence that the mean wingspan of all butterflies of this species is different or is not equal to 4.5, then what we would do is we would say our p-value is 2 times their tail area, and we would take 0.10 and multiply it by 2. And then our concluding p-value would be greater than 20%. Okay? Again, we don't know exactly what it is, but we just say the p-value is greater than 20% in that case. Yeah, question?
So with the t-tests, you don't decide the confidence level beforehand, you just choose it.
With the t-test, yeah, we're supposed to pick an alpha during step 2. Okay? I didn't specify one, so we can assume alpha is 5%. Okay? Yeah, but with t-tests, I mean, confidence levels only come into play when we're talking about confidence intervals. So here I didn't ask you to make a confidence interval. I guess, I don't know if I said anything about a t-test either, but we're doing a hypothesis test, and so you don't need a confidence level. You do need an alpha, and in our case, alpha is understood or assumed to be 5%. Okay. Any other questions? Yes.
So the right tail is equal to 1.09, or?
So, no, this is my test statistic. Here, I'll draw you a picture, and this might help you understand how this t-table thing works. For those of you who are visual, those of you who aren't, and this doesn't make sense, don't worry about it, okay? So the way the t-table works is, you've got this thing. The t-distribution looks very much like the normal distribution. And the idea here is that, let's say we're in this row, 24 degrees of freedom, okay? 24 degrees of freedom, the first value that shows up is 1.318, okay? What we're saying is that if I draw my cutoff line at 1.318, the area over here, this area, is equal to 10%. Okay? If I go further out to 1.711, 24 degrees of freedom, if I go further out to, what's going on here? Okay, 1.711, okay, then the area over here, this is 5%, okay, the column heading. Okay, and if I go further away to 2.064, I should say total area to the right. it's not like the areas in between. And it gets smaller to 0.025. And so that's why as t gets bigger, the area in the tail gets smaller. Okay, and so, in this problem, RT ended up being, what, 1.09 or something, okay? What this is saying is that, and this is just an overly exaggerated picture here, but this is saying that if I shade everything to the right of 1.09, how much have I shaded in? Okay, well, we don't have an exact answer, but I do know that the amount I've shaded in is more than 10%, okay? So I draw a line at 1.09, how much is shaded to the right? Okay, the answer is, we don't have an exact answer, but we do know it's more than 0.1. Okay, that's how this t-table works. Okay, if we have a cut at 1.9, how much have we shaded in? We don't know, but we know it's more than 0.025, but less than 0.05. That's what we're saying. Okay. If this picture doesn't make a whole lot of sense to you, it's okay. Just go with the column headings and you say, okay, well, I'm in between these columns, therefore my area is between these column headings. That's fine. Okay, is that all right? Okay. Okay, so we have a couple other inference methods to deal with for means. We've got confidence intervals for means with 2 samples. Okay. All right, so in this case, we are making a confidence interval for the quantity mu1 minus mu2. Okay, so this is a confidence interval for the difference between population averages. Population means. Okay, we are not making confidence intervals for one population and confidence interval for the other population. Okay, so we've got 2 samples, but we're not making a confidence interval based on sample 1 and a confidence interval for sample 2. We're making a confidence interval for the difference between mu1 and mu2, okay? So let me just note that. We are not making a confidence interval for the mean of population 1 and a separate CI. All right, so, for example, okay, let's say we were talking about the average heights of men and women, okay? Okay, so, we'll say sample 1, we'll say men, sample 2, women, okay? And just without, I don't need to give you any numbers here, just, you know, what would a reasonable you know, 95% confidence interval look like for mu1 minus mu2? Okay? So I want you to think about this. You know, what kind of numbers would we expect to be on the lower and upper bound for this confidence interval? Okay? We're talking about the average heights of men and women. So mu1 will be the kind of the average height of all men. Mu2 will be the average height of all women. So what would a reasonable confidence interval be for the quantity mu1 minus mu2? What do you guys think? Okay, so the idea here, another way we can phrase this is, let's say there was such a thing as the, quote, average man, okay? So just imagine the average man standing here, okay, and we measure this person's height, okay? And then let's say there's something called the average woman, and we have her standing here, and we measure her height, okay? And we're asking, what do you think is the difference between the average man and the average woman in terms of height? Okay? And we would probably say, all right, that height difference is probably what, 5 inches? Something around there? Okay, maybe more, maybe less, all right? And so our confidence interval, like our 95% confidence interval, will probably be something like 3 to 8 inches or something like that. We'd say I'm 95% confident that the average height of men is somewhere between 3 and 8 inches taller than the average height of women. Okay? And so, so we might say, you know, maybe 3 to 8 inches. Okay, I mean that's a fairly wide range, but we would say, you know, I am 95% confident that the average height of men is somewhere between 3 and 8 inches taller than the average height of women. Okay. Now, of course, any individual person, you know, if you pick a random person here and a random person there, their height difference might be wildly different, right? You could have, you know, a negative height difference, you know, very drastic height difference. But this is about the quote the average, you know, the mean height of the entire population of men and the mean height of the entire population of women. And I think we would agree that overall, on average, men are taller than women. Okay, and so, so our confidence interval might be something like 3 to 8. Okay, and in this case, you know, notice we did not make a confidence interval for the average height of men or a separate confidence interval for the average height of women. We're making a confidence interval for the difference itself. Okay. So in this case, if our interval goes from 3 to 8 inches, we would say the interval provides evidence that the average height of men is taller than the average height of women. Okay, what if we went to an elementary school, however, okay? And we go to, I don't know, a 4th grade classroom, and we measure the heights of boys and the heights of girls. Okay. What do you think our confidence interval there would look like?
1 to 3 inches.
Okay. Well, so here, okay, so if we go to, let's say we go to a 4th grade classroom. Okay, and we measure, so sample 1. Here, this time we'll switch the sexes. So sample 1 will be the girls. Sample 2 will be boys. Okay, we're still measuring heights. Okay, we're measure heights. So mu1 represents mean height of all girls. Mu2 will be mean height of all boys in 4th grade. Okay, what would a confidence interval for the quantity mu1 minus mu2 look like? What do you guys think? So in 4th grade, on average, are girls taller than boys, or are boys taller than girls, or do we not really know?
Girls are taller than boys.
It's like, well, I don't know, right? Like, it's hard to say, right? In 4th grade, I don't know. Okay, so I'm not a pediatrician, so I don't really know these. I'm just totally making up numbers. If you haven't noticed this entire class, every example I'm making up numbers here. Okay, but here, if somebody claimed that 4th grade boys are taller than girls, you'd say like, well, maybe. And then if somebody else claimed, no, 4th grade girls are taller than 4th grade boys, you go, I guess that's possible too. Probably, right? Like, I don't think we have super strong, opinions about this or knowledge of the facts here. And so if our sample is small, a 95% confidence interval might look something like -2 to 4. Okay? So what does this mean? Okay? This would be, I'll write out the interpretation. I'll write, I am 95% confident that the mean height of 4th grade girls is between 2 inches shorter and 4 inches taller than the mean height of 4th grade boys. Okay? So we're saying that, if we looked at the average height of all girls and the average height of all boys in 4th grade, all we can say is that, well, it might be somewhere between 2 inches shorter and 4 inches taller, at least based on, whatever sample I might have collected here. Okay? And so in this case, what we notice is that the value 0 is inside the interval. Okay? The value 0 is inside the interval. And so this means that 0 is a plausible value for the difference between mu1 and mu2. Okay, so what does this mean? This means that our interval does not provide evidence that there is a difference between the mean height of girls and boys in 4th grade. Okay? Okay? Does that make sense there? Now, does this mean that there is no difference between the mean height of boys and girls in 4th grade?
No.
No, it does not mean that, right? Because so, you know, a question we could pose is, does your interval provide evidence that there is no difference? Okay? That would be the same as saying, does your interval provide evidence that the quantity is equal to 0, right? And we know that intervals never provide evidence that the quantity is exactly some value, okay? All we can say is that could the quantity be 0? We're saying 0 is a plausible value, okay? And if 0 is a plausible value, then that means we don't have evidence that there is a difference. That's great. Okay, and so this is the confidence interval for the difference mu1 minus mu2. Okay, so here, you know, I started off with the interpretations because I think that's the important part. Okay, so kind of the I guess the quick rules here. Quick rules for a confidence interval for mu1 minus mu2, and is if 0 is not in the interval, okay, this means we do have evidence that there is a difference between mu1 and mu2, okay? And on the other hand, if 0 is in the interval, this means we do not have evidence that there is a difference between mu1 and mu2. Okay, so these are kind of the quick rules for making your conclusion here. Okay, so how do we go about making our interval? Okay, so the interval itself, the confidence interval for mu1 minus mu2. Okay, well, the center, it's always in the form center plus or minus margin of error. Okay, the center is x bar 1 minus x bar 2, okay, plus or minus critical value t star times the standard error. Okay, the standard error, we just kind of have a, you know, slightly messy formula. S1 squared divided by N1 plus S2 squared divided by N2. So you need the standard deviation of sample 1, you square that, divide that by the size of sample 1. Standard deviation of sample 2, you square that, divide that by N2. This is all given on your formula sheet as well. Okay. And then as far as the T star goes, you go to your t-table. You know, pick the, find the confidence level. Okay, and then degrees of freedom is equal to n minus 1. Okay. However, you have two n's. You've got an n1 and you have an n2. So what we do is we use the smaller of the n's. Okay. So use the smaller of n1 and n2. Okay, so use the smaller n, and then you just plug in your numbers and you go. Is that all right? All right, let's. I guess we'll finish with an example, and I guess that will be it for today. Okay, so let's say. I don't know. Do. What is? Okay. Do oranges weigh more than apples? Okay. Or have a different weight from, I don't know. Do oranges and apples have different weights? This is what we want to know. All right, so you go to the grocery store. Somehow you get a random sample. Let's say 10. We'll do 12 oranges. Okay, and what's the mean weight? How much does an orange weigh? The mean weight of an orange, I don't know. It's like this big. It weighs a half pound. Let's ask Google. Average weight of an orange. 131 grams. Thank you, Google. Okay. All right, we'll say 131 grams, and the standard deviation. Okay. All right, Google, that's enough. All right, the standard deviation of these oranges is, I'm going to make this up. I don't know. 15. Yay. All right. And then apples. Okay. I don't know. Let's say we go to 15 apples. All right. And we'll say the mean. All right. Well, I'm excited. All right. Average weight of apples. All right.
0.33 pounds.
Oh, well, that's not helpful if you tell me in pounds. Okay. All right, we'll say, all right, we'll just make this interesting. We'll say large apples, 121 grams, okay? And we'll say the standard deviation here was 20 grams, okay. All right, so make a 95, oh, we're gonna run out of time. Okay, make a 95% confidence interval for mu1 minus mu2, okay? And we'll call the oranges will be group 1, and then apples will be group 2. Should I just do this? All right, all right. All right, x bar 1 minus x bar 2. Times t star times our standard error. All right, standard error. Excuse me. S1 squared over n1. S2 squared over n2. Okay, so we'll go 15 squared over 12 plus 20 squared over 15. What is this? Square root of 15 squared over 12 plus squared over 15. 6.739. Okay, and then, all right, so we go 131 minus 121 plus or minus t star. Okay, so my t star, I've got degrees of freedom equal to, I've got two n's. I'm going to do 12 minus 1, smaller n. So I've got 11 degrees of freedom. 11 degrees of freedom, 95% confidence, 2.201. Okay, so what do I have? 131 minus 121, this is 10, plus or minus, and multiply this by 2.201, 14.83. Okay, so my 95% confidence interval goes from negative 4.83 to 24.83 grams. Okay. Okay, so based on my confidence interval, or my confidence interval does not provide evidence that apples and oranges have different mean weights. Okay. Of course, if we gathered more data or we looked at a different sample, it might provide evidence that there's a difference. But in our sample, we have, 0 is inside the interval. So that is why we do not have evidence at this point that apples and oranges have different mean weights. Okay, we'll end here for today. And this weekend I'll post up a practice final, so you can start practicing and working through that.